I will now go ahead and introduce our speaker, Hannah Gulick. So Hannah Gulick is a PhD student in astrophysics at the University of California, Berkeley, where she builds space-based instruments to study black holes and other extreme objects in the universe. Her work focuses on designing and testing cameras for small satellites that monitor the sky for rapidly changing events like stellar explosions and microgravity. She also has a background in creative writing and enjoys exploring the intersection of science, art, and broader communication. She will soon begin a NASA Hubble Fellowship at California Institute of Technology, where she will continue developing new ways to observe the transient universe. And she did not say in her biology, but that is a really impressive fellowship, so we should really be giving her a huge round of applause, and thank you so much. Without further ado, please take it away.
Yeah, thank you, Daniel. So my name is Hannah Gulick. I'm a PhD candidate here in astrophysics, and I actually graduate in 2 weeks. So I'm finishing up pretty soon. So first, before I start, show of hands, who in this room has an iPhone? Okay, so a lot of the room. Anyone have any Samsungs, Google phones? A couple. Okay, so I'm not going to address your phones. We can do that calculation later. I'm just going to focus on the iPhones today. So as Daniel mentioned, I do a lot of instrumentation, and so this is a very specific genre of astronomy where we're motivated by the science, but we also want to build the tools that we use to do the science. And so my science is focused on detecting stellar mass black holes, so not supermassive, the huge ones in the middle of galaxies, but these smaller black holes that are about the size of the sun, maybe 10 or 20 times bigger, and they're just floating around our galaxy. So there's billions of them in our galaxy alone, but they're really hard to see, and I'll talk about that a little bit. And then to put a fun twist on it, I wanted to do a calculation to see whether or not you could detect a stellar mass black hole with your iPhone. So to start off with, I want to give a little bit of a science background. So how does a black hole form? This is a really big question in astronomy right now, and if you've ever taken a basic astronomy course before, you'll have been taught that your big stars die and create black holes. Your medium stars die and create neutron stars, and then your small stars die and create white dwarfs. And so you then go about believing that if you find a big star, it's going to create a black hole. However, this super complicated diagram over here shows you that it's not really that straightforward. Whether or not you get a black hole depends on a lot of things, like the metallicity of the star before it explodes, whether or not it's in a binary system. So this specific plot, I'm not going to go in depth over here, but it focuses on if you have a binary system, so that's 2 stars, whether it's a high mass binary system, so your 2 stars are big, low mass binary system, so your 2 stars are small, and how far apart they're separated. So if they're very, very far apart, you can kind of treat them as two separate stars that aren't really in a binary system, even though they are. And what you'll see is that there's a ton of different paths, and it really impacts what kind of compact object you're going to get at the end. And so it might not always be a black hole, it could be a neutron star. And we have a lot of questions surrounding this. So some of our open questions are just about the basic properties of black holes. Is there a mass gap between the heaviest neutron star and the lightest black hole in the universe? In addition, the origins, so we just went over this in this plot. How do black holes actually form? Which stars are going to produce our black holes? Third, the population. So I mentioned that we think there's billions to tens of billions of these objects in our Milky Way galaxy alone. But we've only seen a couple dozen of them in these binary systems, and then a single isolated one, so only one free-floating black hole. And then finally, their evolution. So how do we get to these merging events that everyone's very interested in right now? So you have a binary system of 2 black holes that eventually merge together. And just what does it look? What does a black hole lifetime look like? So to answer these questions, I've kind of hinted at it a little bit already. We need to first see these black holes, and this is really, really challenging to do. And I'll explain that a little bit more. And then again, I'll just emphasize quickly that we've detected 1 isolated black hole so far, out of 10 billion. So the next question is, how do we see black holes? Black holes don't emit any light, which makes them very challenging to detect. So your neutron stars, your normal stars, your white dwarfs, they're all emitting light, and they might be faint, but you can still see them. Black holes don't emit any light. And so I'm going to discuss 3 main ways that we can detect black holes that already exist. So not the birth of a black hole, but some black hole that's already out there. The first one is going to be an X-ray binary. So over here you have a black hole, and then orbiting around this black hole, or with this black hole, is a star. It can be a big star, it can be a small star, it just needs to be a star that's close enough that they interact. And what happens is this black hole accretes from this star, and this produces X-rays. And we can see these X-rays, and then we know that we have some kind of system with a black hole inside of it. The next is through gravitational waves. So people might be very familiar with gravitational waves. It's one of the hot topics right now in astronomy. But just to give a quick synopsis here, so if you have a binary system that has a black hole and a neutron star, every object in space has some kind of effect on the space-time continuum. It means it has gravity, it's impacting it somehow. And so if you imagine this like a blanket and you put like a bowling ball on top of it, the blanket's going to curve a little bit. And so that's what's happening in space with all of our objects, and black holes are very heavy such that it kind of curves down to infinity. So if you have two of these orbiting one another, they create these ringing motions, so like a ripple in a pond. And eventually, due to their gravitational force, they're going to slow down and merge. And this is something that's very, very interesting right now. So when they merge, they create this gravitational wave event, which we can detect with systems like LIGO. They also produce some electromagnetic counterpart. This is in a bunch of different wavelengths and things that you can detect with ground-based telescopes, space-based telescopes, and it's called a kilonova. And then the third section I want to talk about is microlensing. So I'm being a little bit misleading here. This is not a microlensing event. This is a macrolensing event. It's a very big gravitational lens. It's a famous photo, but what you see is a galaxy in the center. So this galaxy is actually closer to us. And then around it, it's lensing, its gravity is lensing this galaxy that's much, much further away. And gravitational lensing is a very cool phenomena. It helps you measure the actual mass inside of this galaxy. You can also get properties of this lens too. Microlensing, you can't actually see this image. It's more on the light curve side. So I'll explain that a little bit more in the next couple slides. But I want to just be very clear and separate these into two different categories. Both of these require a binary system in order to detect them. Microlensing is the only way to detect an isolated event. And you really want to be able to detect both of these because if you have binary systems that you're probing, it's telling you specific physics for binary systems. And you need to be able to understand our isolated events as well. Okay, so what is microlensing? Microlensing is a very cool phenomenon where you have some telescope that's on Earth or orbiting around Earth. And if you look up at the sky, we see a bunch of stars. And then if you have some kind of object that passes across what we call the line of sight, so in between your telescope and your background star, what's going to happen is this object is going to lens, let me back up. This object has some kind of gravitational well, and its gravity is going to cause more light from the background star to be funneled into your telescope. So if you're looking at it over time, you're looking at the star over time, what you're going to see is an amplification, and then it goes back down once the object passes. So I'm going to transition this into maybe a little bit more of a scientific figure that we use all of the time. So this plot up here is showing you the same exact thing I was showing in the last schematic, but for more of a face-on view. So you're the telescope here. Right here we have our background star. The red object is the, in this case, black hole that's passing in front of the background star. And then you see that two things happen. This background star does get split into two images, which are these two blue images. If we had better resolving power, that would look something like the Einstein ring in the last photo that I was showing. However, we aren't able to distinguish these right now. So instead what we look at is really this light curve. So this is just showing the brightness of the star over time. And there's two really important characteristics we can get from this light curve. One is going to be the duration, so how long is this event? And then the other one is called the microlensing parallax, or pi-e. And basically the microlensing parallax tells us about the shape of this light curve. If you're familiar with the word parallax, it basically tells you that when you're on Earth, if you're observing something in the sky, the Earth is moving around the sun. And so our observations of this object change as we move around the sun. So if you go outside and put your thumb up and you close one eye or the other eye, it's going to change which stars you're looking at. It changes your perspective. And that has an impact on our light curve where we get an asymmetry in this downward going tail. And the strength of this asymmetry tells us about what kind of object is doing the lensing. So if you take these two different parameters, the duration and pi-e, and plot them against each other, so we have the duration on the x-axis down here, and then your microlensing parallax on the y-axis here, something really cool happens. And because our black holes are much more massive than the other objects, we get our black holes kind of to separate out into this bottom right-hand corner. And so from this plot alone, we're able to kind of identify what type of lens we're looking at, which is really, really important. And this might seem kind of straightforward, but it's really the ideal case because we have error bars in real life. So this image here is showing you the same plot, pi e on the y-axis versus TE on the x-axis, and it's from one of our leading microlensing surveys called OGLE. It's a ground-based telescope that does a bunch of different microlensing observations, but what you really can see here is that the error bars are huge, especially on this pi e parameter. So if you were to try to go in and identify which of these are black holes, we can't really confidently say. And there are many, many microlensing events every year, so it's not realistic to follow up all of these events to see if they're black holes. And this contributes to why we only have one detection of a microlensing event for a black hole to date. So there's a few things we can do to build a telescope that's capable of detecting these stellar mass black hole microlensing events. First, we need a really long duration, so the telescope needs to operate for a very long time. This is because for stellar mass black hole microlensing, it takes about hundreds of days for the event to happen, and we really want to see this entire light curve. In addition to that, we need a regular cadence, which just means that we need to sample very uniformly. So if we sample right here, we want to sample right here, again, all the way across this light curve so we can really reconstruct what its shape is. We also need very small error bars, so I showed you that on the last plot. If our error bars are too big, we can't confidently identify which of these are black holes. We need good spatial resolution, so this just allows us to disentangle which is our variable source on the sky and which are background sources. And then we need a moderate field of view, which just means that we need to be able to see a big chunk of the sky at any given time. So the question I think everyone's here for is, can we do this with an iPhone camera? And I'll get to that, but I'm going to open this up to the audience for a minute, and I'm going to ask, why can't you just send an iPhone into space and have it work? That's a big one. So the second you leave the atmosphere, you've got radiation coming in from a bunch of different components. The component in your basic iPhone, the components in your basic iPhone are not built to handle radiation, so they're going to die. And you're exactly right, you're going to get a couple days out of it and it's not going to work. Any other thoughts?
Lack of light.
Lack of light, so we need to make sure we're picking the correct camera in order to detect these very, very faint objects. Exactly. Any other thoughts? Yeah.
Freezing temperatures.
Temperatures are another big one, so we need to test and make sure that your components can actually exist at the temperature fluctuations you're going to get on orbit. Any other ones? I'll give you a hint. Look at this photo. This is specific to this photo. So we want to make sure we set it up in the right way too, and that our camera is actually pointing towards the telescope. Right now, the telescope is. Sorry, let me back up. So your camera should be inside of this CubeSat bus, and your telescope should be pointing out to space. We're actually completely blocking our field of view right now in this image, which just means ChatGPT doesn't know how to build a satellite. Another big one was, is it going to fit in the satellite? So satellites are small. It's expensive to get them into space, and so we really, really optimize for making things as tiny as possible. In addition, it needs to have very minimal mass. Mass is expensive to get into space. Before I go on, did anyone else want to contribute? A couple others. Yeah.
A lot of extra junk that's not necessary.
Exactly. So we're going to cut it down. Okay, so will it survive in space temperatures? We had that one. How much power does it draw? Power is a huge concern on orbit for a couple reasons. Our satellites don't produce a lot of power, but also anytime you're consuming power, you're emitting heat. And when you're in a vacuum, you don't have convection to take away this heat. So thermal management is one of the biggest challenges you'll run into when you're designing a satellite. On top of that, can it withstand radiation environments in space? Will it survive vibrations? We have to get it into space. When you put it on a rocket, rockets shake really hard and components can fall off and a bunch of different things can go wrong. On top of that, does it use vacuum-safe materials? So if you were to go into vacuum and just use Elmer's glue or a normal type of glue, what's going to happen is it's going to outgas, which means it emits a bunch of particles, and these particles are really bad because they make everything really grimy, and they can get on your optics and your detector surface, and it just reduces your performance catastrophically a lot of the time. And then finally, this is a big one, this is a really hard one, does it speak the same language as the rest of the satellite? So can your satellite support USB, for instance, right? We send a lot of information over USB on our phones. USB is actually not used in space very often. I know this very personally. It's hard to do. And so picking something that uses a safe language for space is also very important. Okay, so summarizing this list a little bit in this table, I do just want to be maybe a little bit pedantic and tell you exactly what a space grade camera is. So there's 3 different types of components you can use. There's your space grade components, your automotive grade, and your commercial grade. Your space grade are completely rated to go into space. They can withstand radiation. They exist at a bunch of temperatures. Your automotive grade exists at a bunch of temperatures, but they don't really have radiation capabilities. And then commercial is not really built for either of these. And so if you have a space grade camera, what they typically focus on is that they're compact and low mass. They're going to fit in your bus, your satellite bus. They're radiation tough and temperature hardy. They use safe materials, and then they have specific communications that they're using. However, they're typically pretty small. So this MP right here means that they have 20 million megapixels, which sounds pretty big, but you can get up to about 200 megapixels for detectors in this day and age. And when we're doing these all-sky surveys to detect stellar mass black hole microlensing, we want to be able to cover as much of the sky at once, which means that we want a really big detector. And then if we try to get a really big detector, it's going to be really expensive. And so if you're trying to build a low-cost satellite like a CubeSat, $500,000 is way too much. So if we go to the commercial side of things and look at an iPhone, for example, it's about $1,000. They have 48 megapixels, so million pixels, but they don't qualify in any of these other categories. And so my question during this talk is, can we kind of put it through its paces and use this as a checklist to get it prepared for space? So step 1 is that we need to pick our camera. And so I'm showing you some characteristics over here that are useful to use to pick a camera to send into space. We had the comment about whether or not it can actually detect the light we're trying to see. I'm going to go through each of these a little bit in detail to tell you exactly what you're looking for in a detector. So first is the number of pixels. This one might seem pretty straightforward, how many pixels are inside of your detector. And this photo here emphasizes that getting more pixels does 2 things for you. 1, it can make your image bigger, which is great. You can cover more of the sky. And then 2 is that it increases, okay, I don't know why I did that, but it increases your resolution. So how good does this image look? So this one is pretty blurry over here, and then over here you can see that this galaxy actually has spiral arms, and there's some kind of bright object right here. Here, it's just a blur. And so getting more pixels allows you to see more and to see better a lot of the time. The next one is, I'll add here though that anytime you optimize for something, you're giving something else away. So when you get more pixels, your detector gets bigger, it takes up more space, it takes up more mass, and a lot of the times it takes more power too. And so a lot of doing instrumentation for satellites is doing this trade-off of how many pixels do I really need to accomplish my science without overwhelming the requirements for my satellite. The next one is going to be pixel size, so how big are these pixels on the sky? So this specifically impacts that spatial resolution that I was talking about before. And spatial resolution just means how close can 2 stars on the sky be to one another, and we can still tell that they're 2 different stars. And so this photo on the left is showing you an image from Hubble, and the spatial resolution is much, much higher than the photo on the right, which is from Spitzer. There's some other different characteristics here, but I just want you to take away that up here you can see that there's 3 main galaxies, but then there's a few smaller ones around it. Over here in the Spitzer image, you would just say that there's 3 galaxies right there. So, as you're waiting for, there is a trade-off here too. The smaller your pixels get, the less light they collect. And this is a problem because when you go to signal to noise ratios, so how much signal do you have compared to noise, it means that our ratio to noise gets higher. Or sorry, how much noise we have in each of our images gets higher. The next is going to be your pixel array. So what shape is our detector? Is it a square detector? Is it a rectangular detector? And this basically just affects what our field of view on the sky is going to look like. So I'm showing you 2 different major missions right here. This funky shaped one is Roman. That's because they use a bunch of different detectors and kind of stitch them together. And then in the center we have Hubble, which is a very famous optical telescope. And there aren't many trade-offs here. I think a lot of people don't really optimize for their pixel array shape. It can be helpful to have squares for analysis purposes, and as well as just doing tiling across the sky. The next one is going to be the number of cameras. So this is a schematic of Hubble, and Hubble has a bunch of different cameras on board that all do separate and unique things. They're all very powerful in their own sense, but you don't often overlap a bunch of science cases between them. The iPhone, so I have an iPhone 15 for example, there's 3 separate cameras inside of your iPhone. There's a wide field CMOS, the normal CMOS, and then there's a telephoto lens that does the zooming. In this case, we're only going to focus on the main CMOS. The other 2 aren't great applications for space, but if you could make it work for space, then you'd have a powerful 3-camera system. And then finally, I'm going to skip over these last 2 because we talked about them, but you really care about mass and you really care about volume. Okay, these are just some other characteristics too that I didn't go into that I'll just run through. You care about your bandpass, what part of the electromagnetic spectrum you see. You care about the quantum efficiency. So for every photon coming in, what percentage of them do we actually detect? You care about shutters, if it's rolling, so your pixel rows read out one after the other, or if it reads out the entire detector at once. You have things like back and front side illuminated, noise properties of your detectors, data transfer type, power draw, and also the thermal properties. So this is a table showing you these characteristics for different generations of the iPhone. So it's going all the way back to 6. We have iPhone X, 14, 15, and then the 15 Pro Max. And then I've highlighted here which one. This is exactly what I do when I'm picking a detector too. I just make a giant spreadsheet of all their characteristics, and then I put the ones that are best in green. And then whichever one has the most green boxes, we go with that one, unless it doesn't meet requirements in some other sense. But in this case, we're going to go with the iPhone 15 Pro Max. It's got 48 megapixels. It's a pretty big detector. The array is about squarish, which is good. The pixels are 1.22 microns, which is a happy medium between our 1 micron over here and then our 1.9 micron here. We've got 3 cameras in there. We're not going to use all 3, just one of them. And then the mass and the volume are the biggest out of the other ones, but it's still pretty small on the scale of CubeSats. So going forward, step 2, what we want to do is disassemble this camera. So someone said get rid of all of the extra things that we don't need. And the biggest advice I can give you here is use what already exists. So I found this YouTube video online from iFixit, and they go in and they take apart the iPhone 15 Pro Max and show you everything inside of it. They do it so that they can rate how easy it is to fix this iPhone, but for me, it's good if I want to launch it into space. So this is what the iPhone 15 Pro Max looks like on the inside. Up here is where we have our camera. It's super, super tiny, so we're really not worried about mass or volume in this case. And then we want to get rid of essentially everything else inside of this bus. Some of it we need, like a battery supply or communications, but we're going to replace it with things that are space grade and we know how to interface with. Yeah.
You just sort of mentioned bandpass or spectral capabilities in passing. I mean, these phones are optimized for basically terrestrial environments with a person viewing at the other end. I mean, what if you're interested further out towards the UV?
Yes, so it would not work for the UV. You're exactly right there. These phones are, so inside of the CMOS, each of the pixels have different filters on them. So there's a red, green, and blue filter. This allows you to take very powerful color images. We don't really care about color images in space because it all comes back as black and white. So if you want to get really fancy, you can pop those filters off and just take the actual CMOS array, depending on how much money you want to spend, how much risk you want to put into it. These are not optimized for UV. We would definitely need a different detector for it. But in terms of optical, they cover a similar bandpass to other equipment that I'm working with right now. So in that sense, they fit the bill.
So for the targets you have in mind?
Yes, good. It'd be better if we could go into the infrared for the targets that I have in mind, because you can see through the dust in the Milky Way's plane. But infrared detectors are really expensive, and so we've stuck with optical so far. And I'll comment a little bit more on that in a few slides. Okay, so as part of this step 2, it's not just important to get rid of all the extra tech that we don't want. You also want to get rid of these scary and bad materials that are only going to cause you problems in vacuum. So I watched through this video and I took a screenshot every time I kind of jumped and said, oh, I would not put that into vacuum. They use a lot of different glues, a bunch of elastic things. The whole battery pack here was glued down, and then you can see that these screws are pretty dirty as well. So step 3 is going to be test, test, test. So we found something. It meets a bunch of the requirements that we need in order to detect a black hole, but is it actually going to work? And so this gets into the radiation environment and the temperature environment as well. So at this point, you're probably wondering, do we actually do all of this work, or is this just a thought exercise? And yes, so this has been a big part of my PhD. I'll share a little bit more about what exactly I've been doing. It's not been with an iPhone, but it was very transferable to this specific topic. So I'm going to transfer to what I've been doing in my PhD. So we have our space grade camera over here. And then we wanted a specific detector. And just to back up a little bit, I've been using the word detector and camera a lot. There's a big difference between the two. Detector is just your detecting surface. So it's a chip that you can get from Sony. There's one inside of your iPhone camera, but it's not the camera. The camera is actually the electronics that read out the detector to give you the image. So there's a really big difference there, and it was very confusing for me when I started this. So we found a specific detector that we wanted to use on this CubeSat mission to detect stellar mass black holes. It's a very big detector. It's 61 million pixels. It's got small pixels, so we have good spatial resolution. However, it was brand new when we started doing this project, which meant that any space grade version, one, didn't exist, and two, would be incredibly expensive if we tried to do it custom. And so we said, hey, what if we just buy this commercial camera that you use for ground-based amateur astronomy, and then use this as a checklist to space qualify it? And that's what I've spent the past few years doing. So this is showing the original packaging. This is showing it when my advisor gave me a screwdriver and let me loose to take it all apart. And you can see here we have some extra text. So there's a fan right here. Inside of it, there's this fancy Peltier cooler. And then the casing is really big and bulky. And what we found was a black box. So this just means that we don't have a good understanding of what's on the inside. Even though we can see the PCBs, the electronics boards, there's a lot we have to learn. A lot of it is proprietary. We didn't build it ourselves, so we don't have an intimate knowledge of what's going on in the system. So it took a lot of kind of reverse engineering and backwards testing. So I'll just highlight a lot of the changes, or the biggest changes that we made to this camera to prepare it for space. First, we removed all that additional tech. We don't need any coolers in space. Fans don't work. You don't have convection in the vacuum, and so that wasn't going to be useful to us at all. In addition, we removed the outer casing, and all of this functioned to reduce the volume and the mass by quite a bit, such that we could now fit it inside of our CubeSat bus. Sorry, am I using CubeSat liberally? Do people know what CubeSat is? A little bit? Okay. So CubeSats are just very small satellites. They're about the size of a shoebox or a bread box, and they allow you to get science into and out of space for lower costs than doing a major NASA mission. Okay, so going back to the camera now, we also removed unsafe materials, so those glues and things that I was showing you in the last couple slides. We took off a lot of the connectors, so this camera came with a USB connector and a power barrel. You can't really launch these into space and be confident that vibrations aren't going to take your cables out of them, that they're actually going to work in the space environment. So we cut those off, and then we soldered on a specific space-grade cable that goes to a safer locking connector. And this allowed us to be a lot more confident in our ability to communicate and supply power to this camera. On top of that, we conformal coated our boards. And this just means that we essentially took them, once they were done, dipped them in plastic and pulled them out. And what this does is it holds all of the components on the boards when you go through vibration so they don't accidentally shake off or short to one another. It's a big safety precaution. And then I was mentioning earlier before the difference between space grade, automotive, and commercial. These are commercial cameras. The vendors never meant for them to go into space, but the vendors are fantastic and they want them to go into space. And so they actually worked with us to swap out most of the components from commercial to automotive grade, which gives us a lot of bandwidth with the temperature fluctuations. And then this is a really ugly box. It was my first mechanical task that I did, making this box. It's not what we're going to launch into space, but it's what we did a lot of our testing in. And then after we did all of these modifications, we did a ton of testing. And so I'm going to go into each of these different ones and explain to you a little bit about why we do it and what you actually do to do the testing. So first things first, you usually start with a thermal vacuum. So I'm going to call this TVAC, which stands for thermal vacuum. And essentially, once you're in space, you have a bunch of different temperatures that you're experiencing. So you're orbiting around the Earth, your satellite's orbiting around the Earth. When you're in the sun, the satellite gets hotter. And when you're outside of the sun, you're being occulted by Earth, the satellite gets cooler. So that makes sense. Another thing is that your electronics consume power and produce heat. And this is a really big one. Self-heating is something that's hard to control and takes a lot of thought to fully understand. And you definitely have to test it in thermal vacuum before you launch anything. So this here is showing one of our camera boards. And then this is showing an IR photo of this camera board. And what you can see is that the FPGA, which is this chip right here, is pretty hot. It gets up to about 70 C when we're running it in the lab. And then this chip over here is also pretty hot as well. And so when we're putting this into a space package, we want to put some special care into making sure that we have a route for the heat coming from the FPGA to get into deep space. And you typically take some kind of metal like copper and just attach it to a radiator, and then this heat can be emitted out into space. So the purpose of the TVAC test is then to see whether or not our instrument can actually work on orbit at all of the temperatures we expect. So this is what a typical TVAC test looks like. We're using here, this TVAC chamber is called Snout 1. All TVAC chambers have a name. If it doesn't have a name, you shouldn't use it because it means no one's given it a little TLC, and you definitely want to make sure that your instrument's taken care of in there. So this is Snout 1, and it's up at Space Sciences Laboratory. Inside of the chamber, we had our camera set up right here. This is using that same box I was showing you before. And then on the front of it is wrapped aluminum tape. We used this just because we wanted to have a dark environment so we could measure the noise characteristics of the camera. And then TVAC is a really long test. It takes about 16 to 20 hours. This is because you can only heat and cool your system so rapidly without potentially damaging it. And so it's a lot of team bonding. You make sure they go friends around, your team's around, and then you do work, you watch movies and you chat, but you take a lot of data at the same time. And then for this specific test, we ran the chamber from -35°C up to 40°C, and we did it 4 separate times to prove that it would work continuously and not just one time. The next test we do is radiation testing. So it was mentioned that radiation is a problem. So if you can survive thermally, if you handle your thermal conditions well, radiation is going to be your biggest enemy on orbit. And a lot of the times this is really the lifetime limiter for your satellites if they exist long enough in space. So you get things, radiation from things like the Van Allen belts. You get it from cosmic rays coming from supernovae super far away in different galaxies. You get it from the sun, and then you can also get it from secondary neutrons, which are produced even within your satellite. So what does the radiation do? When it interacts with your electronics components, it can cause temporary faults where the electronics stop working for a little bit, but if you power them down and power them back up, they'll start working like normal. It can cause catastrophic faults where it comes in, it latches up your instrument, and then it never recovers. And if it doesn't do either of these, it is going to degrade the performance of your instrument over time. And you'll see this in the way it's taking data, but we have a lot of ways that we can adjust for this and kind of address it once it's on orbit. So this is showing the test that we did for the specific camera that I've been working with. The camera is right here. We have a fan pointing at it because we're not in vacuum for this test. It's just in air, and we wanted to make sure the camera stayed cool enough. And then we have a proton beam over here. And what we did was we irradiated it or shot enough protons at it to simulate 5 years in low Earth orbit outside of the radiation belts. And we monitored whether or not the camera could survive all of this, if it had any issues, and it did have a couple issues, but they're things that we can address. And then eventually got to the point where the camera survived, which none of us really expected it to because it's a commercial camera. This one does not have the automotive grade parts, it was just commercial parts. And it's still 1 floor up working to this day, and we use it for a lot of testing, which is really exciting for us as well as ADIC, the vendors of this camera. And then I'll point out that some of the most exciting images I think we've gotten, which aren't necessarily good news, but they're cool to look at, were during the beamline test. So this image here is showing you an X-ray image of our electronics. So we did 2 different pointings during the beamline test. One time the beam was going into the detector and then through our other electronics boards. And then the second time we had the beam coming in through the electronics boards and then into the back of the detector. When we were in this orientation, what happened is the protons interacted with the electronics in our 2 back boards, and it got imprinted onto our detector. So we took an X-ray of our electronics. The bad news here is that we can still see it even when we're not in the beam, which means that we had permanent damage in the pixels. I will note, if anyone's interested in these Sony detectors, we don't think it's a detector issue. We think it's a specific camera issue, so this commercial camera. They weren't built to survive this radiation. But either way, we do expect to see this on orbit. Okay, so the third thing that we do, our final environmental test, is going to be vibration testing. So this image doesn't make this look as intense as it actually is. Vibration testing is one of my least favorite things. You baby an instrument for years, and then you have to strap it onto this table and allow it to pull 35 Gs. It doesn't make a lot of sense, but you have to do it because you're going to launch in a rocket. Let's see, I think I'm here. Okay, so this plot is a little bit busy, but I just want to show you kind of what we're looking at when we're doing vibration testing, and I'll point out what the success criterion are. So this plot here is showing you something we call a sine sweep. So you put in frequencies, and then you put in a certain load, and then you just increase the frequency from 20 up to 2,000 hertz. And then you measure what the response with accelerometers of your payload is. And so these 2 peaks here are this sorry, these two lines right here are the ones we're interested specifically in this axis. And what you want to see is that your peaks are above 150 hertz. Don't ask me completely why, this is just the requirement I was given. We've got a couple people who might be able to say why. And then you also want to make sure that if you do, let me back up. So you do your sine sweep, and then you do a random vibration, which is where you pull the most G's, and then you do another sine sweep. In your pre and post random vibration, you want to make sure that this peak matches within 5%. If it doesn't, it means that some kind of mass shifted inside of your system, and this is not trustworthy. We do not like that. And this is kind of what it looks like if some of your mass shifts. So we have a nice peak here from the pre-sine, and then this is the second peak after we do our random vibration, and there's a big difference. We actually took this data the other day. It was very sad to see that happen, and then it can get even worse than that if you push it. So this is bad, and the one up there is good. So after all of that testing and the modifications to this camera, we changed our list from all X's to pretty confident, and then some that we do think that we can send this camera into space, get data down from it, and have a decently long lifetime with it, which is super exciting. And then I'll just comment a little bit more about this mission. So I did all of this testing for a broader CubeSat mission called Curiosity, which stands for the CubeSats for Rapid Infrared and Optical Surveys Exploration Demo. Curious is a bigger constellation idea for 300 CubeSats to look at the entire sky all of the time. However, you need a lot of money to do that. And one way to make your funders more confident that you're actually going to succeed is to do a technology demonstration first to show that your technology and your mission works. So this is specifically what Curiosity is. Back here, we have this camera that I've just been talking about repackaged in a very fancy and nice camera housing. And then we bought just a commercial space-grade telescope from Samara, as well as a commercial space-grade computer. And that's all of the components that we use for this mission. And this is showing the final Curiosity product right here, integrated into this 12U CubeSat bus. So that would be 20 by 20 by 30 centimeters, about the size of a shoebox, up in Canada with our collaborators. It's not currently integrated. We're working on another iteration of it right now, but this is what it'll look like at the end. And Curiosity has shown that your low-cost commercial components for space actually do cost a lot of money. It costs in time, it costs in creativity. You need to figure out how to really package these components in a way that they're going to survive. But while they are riskier, you can actually build a space-grade instrument out of them. Questions?
So in this prototype, the optics was pre-space certified?
Yes. Yep. So these optics, Samara has had customers launch these optics before. The thought for getting this optic in this computer is that we wanted to focus all of the risk inside of the camera. And so we wanted something that we would trust would work to get, once we get into space, we could really see how long this camera will survive. And then one exciting thing I forgot to mention, this launches in February this year. So hopefully we'll start getting data back from it soon. 2027, February 2027. Okay, so now to get back to the part you've all been waiting for, can we actually use an iPhone camera, if we package it correctly, to detect a black hole through microlensing? And I'm going to make you wait a little bit longer because there's a couple performance characteristics that we need in order to determine whether or not we can detect a black hole. So this plot here is showing you, I forgot my axis, but it's showing you the signal to noise resolution as a function of your source's magnitude. So I'll break both of those down. Your signal to noise resolution is just showing you what the fraction of signal is compared to the square root of the noise. So if you take a longer integration, a longer exposure time, you're just viewing for a longer time, your signal is going to go up, and then your noise is going to go up like the square root of noise. And so you can actually get better signal if you take a longer exposure, or if you reduce your noise is the other way. And your noise comes from things like sky background, thermal inside of your system. Most electronics like to behave at cooler temperatures than hotter temperatures, and then what type of detector that you're using. So this plot over here is showing you as a function of source magnitude, so how bright our star is on the sky, where these lower numbers actually mean brighter. This is also in log scale, so it's a very vast difference in brightness. What our SNR will be for specifically Curiosity, this not the iPhone camera, but the other camera. And then these lines here are showing you our confidence intervals. At SNR 3, you kind of have a detection, there's no error bars on it, you aren't totally confident, but you think it's there. SNR 5, it gets a little bit better, and then SFR 10 is, yes, we're very confident that we have a detection. There's really no evidence that it can't be. And so to break this down a little bit, If you're up in this left-hand part of the plot, it's too bright. It's going to saturate your instrument and you're not going to get a good detection anyways. If you're in this definitely detectable regime, you're going to get your good detections. If you're in between 5 and 3, you'll get detectable with uncertainty. And then if you're below 3, it's really not a detectable source. In 4, our black hole microlensing, we really want to be probing below 20th magnitude. So a lot of our leading space-based instruments right now function up to 18th magnitude, but we want to go a little bit deeper than that and see a little bit more. And then you can see we cross, specifically for Curiosity, this 10 sigma line, or 10 SNR of 10 line at about 22nd magnitude. So we're going well beyond this. We're in log scale here. If we do this for the iPhone, I'm plotting again, Curiosity's limiting magnitude is what we call it right here. For the iPhone, we're getting down to about 21, which is still really good for a $1,000 piece of technology. And so this is a success. It meets our criterion for doing stellar mass black hole microlensing. The next thing I'm going to point out is your field of view. So I've shown this image before. We're looking at Roman's field of view and Hubble's field of view. For stellar mass black hole microlensing, we want a decently big field of view, so we increase the probability and increase the number of stars we're looking at that we actually see some kind of microlensing event. And so I'm going to shrink this a little bit because our field of views are actually going to be a lot bigger than this. This is what our field of view would look like if you're using that same Samara telescope that we use on Curiosity for an iPhone. So you have a field of view that's about 1 degree by 0.7 degrees. So we're already much bigger than Hubble and Roman. And I want to be clear, this is not to say that an iPhone camera would be better than Hubble or Roman. These are leading astronomical telescopes. It's just that we're able to achieve a bigger field of view here. And then if this is how big Hubble, Roman, and the iPhone would be, this is how big Curiosity's field of view is. So this is what we're able to achieve with that really, really big detector. Okay, so finally putting all of these together, we can now simulate, use simulations to predict how many black hole microlensing events are detectable with Curiosity as well as an iPhone. So the software uses Popsicle. This was created here by Jessica Liu and her grad student Casey Lamp, who's now at Carnegie Observatory. It's a fantastic simulation code. I really like using it. And then you input things like the field of view, which we just calculated, what location on the sky you're looking at. So for black hole microlensing, you really want to look at dense regions on the sky to increase your probability that you'll see a lensing event. You want to look at your pixel size on sky, so how much of the sky can an individual pixel see? What's your resolving power? How long is your survey? Remember, we want a long survey so we can detect these 100-day events. And then cadence, so how fast are you sampling along this light curve? And then I put this here just to remind you what a microlensing event looks like. And then one other reminder is we have the TE parameter and then pi e, which is the shape of our light curve. And this again is showing your TE versus pi e plot, and this is simulated events. I'll show you on the next slide for Curiosity here. So we have our black hole population down here, neutron stars in blue, white dwarfs, and then stars in yellow. And then this is what it would look like for an iPhone. However, this is not realistic. We need to add in our error bars, and we can simulate these as well. So specifically for this calculation, we use a Fisher matrix error bar calculation, and this is then what these plots look like. So it gets a bit messier, but for Curiosity, you can really see that your error bars are small enough to confidently say that we have a black hole region down here where we are seeing black holes. It's kind of the same for the iPhone as well. If we go through and do some more calculations to determine which of these are actually detectable, for Curiosity, we get about 45 black hole events per year, which is pretty revolutionary when you remember we only have one to date. With the iPhone, does anyone want to guess how many we can get? 6, that's pretty close. Factors of 2 don't count, and we get about 1 to 2 to, we'll say 3 per year with an iPhone camera. Which isn't great. You're not going to get a lot of funding sources to give you a couple $1 million to get 1 or 2 black holes per year. But I do think it's pretty incredible that we're all walking around with some tech right now in our hands that's capable of detecting black holes from space. Okay, and then I just want to quickly summarize what the differences between Curiosity and your iPhone are that allow Curiosity to detect so many more black holes per year. A big one is going to be your field of view. So even though our field of view is bigger than Roman and Hubble Space Telescope, it's much, much smaller than Curiosity, so we're just not seeing a large fraction of the sky with our iPhone 15. Additionally, our limiting magnitudes are different. Remember, this is in log scale, so there's actually a big difference in brightness between 22nd and 21st magnitude. But the biggest one is going to be this resolution. So this comes down to the pixel size for your iPhone. We selected 1.22 arc seconds, or 1.22 microns. This correlates to us seeing 0.43 arc seconds, which is a astronomy term for how big something on the sky is per pixel. And this is really small. And this is actually not good for microlensing because you're trying to lens background light. And when you resolve too far, you're removing a lot of this background light, and so your sources get dimmer, or your events get dimmer, and then our limiting magnitude is also not as good. So between this one and this one, that's really what's restricting how many black holes we can detect per year. Another one is detector noise. We specifically picked a detector that has very low noise characteristics. The iPhone is a bit worse. It's good for the ground, but not super great for space. And then our cadence is going to be about the same for these two. And with that, I think I'm going to wrap up right here. I'll thank you and take any questions. I'll quickly summarize though and say that you can find a black hole with your iPhone camera. It's not going to be many, but if you were to set it up properly, follow the right recipe, you could send it to space and see a black hole. Commercial CMOS cameras are very powerful. That's what's inside your iPhone. That's what's inside of Curiosity. And I do want to put a little disclaimer out there that while I simplified this down quite a bit, it's very hard to get things into space. I've spent 6 years trying to do this, and I have yet to launch anything, though they're both coming up, but it's not impossible. And then finally, I didn't talk a lot about this, but I'm always happy to talk more about this curious constellation concept, where we want to launch a bunch of CubeSats to look at the entire sky all of the time, to do science around the death and afterlife of stars. So thank you.